Welcome to Maths with EJD. In this video, I take the last part of constrained optimization methods. Constrained, constrained, constrained optimization methods. All right. So previously, we have looked at the Lagrange multiplier, followed by another method that uses simplex and Lagrange called the sequential quadratic programming. And then right now, our attention shifts to um, interior point methods. Interior point methods. Okay. Like I said already, this is taken care of. This is taken care of. Now we go for this. Interior point methods. Interior point methods. Okay, so interior point methods, the IPMs for short, are a class of algorithms used to solve linear programming, linear programming, or LP, and convex optimization problems. In the next video, I'll be focusing solely on convex optimization, right? So to solve linear programming and convex optimization problems. Okay. Now, um, unlike the simplex method, I have like 55 videos on linear programming which you can check out, and part of it is simplex method. Unlike the simplex method, which moves along the boundary of the feasible region, moves along the boundary of the feasible region, interior point methods approach the optimal solution, approach the optimal solution by traversing the interior of the interior of the feasible region. That's why it's called interior point method, right? The interior of the feasible region. Okay. These methods, and that is the interior point methods. These methods are known for their efficiency in large scale problems. So they are very good for large scale problems. And and they they are particularly popular. They're particularly popular in solving linear programming problems. And convex optimization problems with constraints. And of course, we are in the last three videos, we've been talking about constrained optimization methods, right? So that is why IPM is featuring again. Now we can then talk about basic concepts basic concepts of interior point methods. Okay, so the idea behind IPMs is to iteratively move towards the optimal solution by staying strictly within the interior of the feasible region. Okay, the method works. The method works by solving a sequence of linearized versions of the original problem using Newton's method. We saw Newton's method under gradient-based method. Using Newton's method or other optimization techniques. Gradually approaching the optimal point. Okay, in that situation, consider a general linear programming problem. Consider a general linear programming problem, which is to minimize C transpose X subject to AX less than or equal to B, where X itself is greater than or equal to 0. So where X is the vector of decision variables, A is a matrix of coefficients, B is the right-hand side vector, and C is the vector of objective coefficients. Okay. Now, the method introduces a barrier function. So I think we're still going to talk about penalty and barrier methods later. So the method introduces a barrier function. So barrier function underline. The function introduces a barrier function that ensures the iterates stay strictly inside stay strictly inside the feasible region. That is, it penalizes solutions that approach the boundaries. of the feasible region. This is often achieved. This is often achieved through a logarithmic barrier function that is added to the objective function. Okay, so let's talk about the barrier function now. So barrier function, that came up. The barrier function for a problem with constraints x greater than or equal to 0 is, that constraint means that x is always non-negative. It can be 0, it can be positive, always non-negative. So with constraint x greater than or equal to 0 is given by phi of x, which is equal to minus summation from I equals 1 to n of log x sub I. So that means we have minus into bracket log x1 plus log x2 plus log x3 up to log xn, right? So this function, that's where the whole barrier thing comes from. So this function blows up, that is, goes to infinity as xi approaches 0, because log 0 is undefined, right? As xi approaches 0, ensuring that the iterates stay strictly. So that's the barrier. That's where the barrier thing comes from. So iterates stay strictly within the interior, the interior of the feasible region. Okay. Then we talk about primal-dual. I made mention of, I talked about primal-dual. Like I made a couple of videos about it in the linear programming playlist. You want to check that out. Primal-dual interior point method. Primal-dual interior point method. So one popular implementation of interior point methods is the primal dual interior point method. Okay. It solves the primal and dual, solve the primal and dual problems simultaneously by introducing slack variables. So, we came across the idea of slack variables starting from when we were talking about graphical solutions and then simplex methods. So by introducing slack variables to transform the inequality constraints, into equalities. Okay. So for the primal problem, for the primal problem, we have to minimize C transpose X subject to AX equals B. That's inequality constraints. I mean, that's equality constraints, and then X greater than or equal to 0, maintaining positivity. Then so that's for the primal problem. The dual problem, for that primal problem, the dual problem is, the dual is a transformation of the primal. I explained that also. So here now it will now be to maximize. So if the primal problem is to minimize, the dual is to maximize. If the primal is to maximize, the dual will be to minimize. So here we are minimizing C transpose of X. So here, the dual will be to maximize B transpose Y. I know that B is coming from here. So B transpose Y, and then it will now be subject to A transpose Y plus slack variable S equals C. And then here we now have that slack variable S is greater than or equal to 0. So where Y is the dual variable, of course, X is the primal variable, where Y is the dual variable, and S is the slack variable. The primal dual interior point method solves both these systems simultaneously using a Newton's method. And one thing we know about Newton's method is that because it uses both the gradient and the Hessian of the function, it converges very fast using a Newton's method. Okay, so let's go and talk about the worked example. So example, so use the primal dual interior point method to solve the following LP problem. That is to minimize C transpose X, which is equal to 3x1 plus 2x2 subject to x1 plus x2 less than or equal to 4, x1 is greater than or equal to 0, x2 is also greater than or equal to 0. Okay, so to take care of that now, um, we can formulate the problem using slack variables. So here we say let S1 be the slack variable for the first constraint. Okay, in that case, instead of that first constraint, instead of x1 plus x2 less than or equal to 4, we now have x1 plus x2. Okay, I guess it's important to just switch over here for effect. So we have x1 plus x2 plus s1. X1 plus x2 is less than, the sum is less than 4. So if we add something to it, we can balance it up. So we have s1, that will now be equal to 4. And then we now have the other constraint. You still have x1 greater than or equal to 0. We have x2 greater than or equal to 0. In addition now, we have s1 greater than or equal to 0. So at each iteration, the primal dual method, the primal dual method iterates over the following system of equations. Okay. First of all, it goes over the primal constraint equation, primal constraint equation, where AX is equal to B. Then number 2, it goes over the dual constraint equation, dual constraint equation, where we have A transpose Y plus S equals C. Then number 3, we have the complementary slackness. Complementary slackness. So where we have Xi, Si equals mu. So here, where mu is a parameter that guides convergence. So this method adjusts X, S, and Y. Now we are going to finish stuff with Python. That's why I'm not bothering. Like if you want to understand Newton's method, you can check the previous video. If you also want to understand linear programming and other methods we use, like graphical solution and a simplex method, you can also check the playlist on linear programming. So this method adjusts X, S, and Y iteratively to minimize the objective function while ensuring the constraints are satisfied. So we talk about the convergence and stopping criterion next. Convergence and stopping criterion. Of course, we know what this can be. It can be a number of iterations as a stopping criterion, like do 50 iterations and stop, or if the solutions are consistently the same, then you can stop. So we are going to use Python code to take care of this. So the algorithm proceeds until the difference between the current solution and the optimal solution is within a given tolerance. Typically, stopping conditions include 1, primal feasibility. Primal feasibility, when the primal is feasible, that is AX is equal to B and X is greater than or equal to 0. Then we also have dual feasibility. Since the problems are solved simultaneously, dual feasibility, where A transpose Y plus S is equal to C and S is greater than or equal to 0. And lastly, we have the complementary slackness. Complementary slackness. In this case, Xi multiplied by Si is equal to mu. So as the iteration progresses, as the iteration progresses, the iterates, the iterates converge to the optimal point, to the optimal point. Okay, before we check the code out, let's see some advantages, right? Advantages of interior point methods. So number one, we talk about its efficiency. So interior point methods are more efficient than simplex for large-scale linear programming problems. Then we talk about the polynomial time. So, I mean, that talks about time complexity in algorithms, right? So, polynomial time, they have polynomial time complexity, which makes them suitable for solving large problems that simplex may struggle with. Then we have wide applicability wide applicability. So interior point methods are applicable to a broader class of optimization problems, including quadratic programming, semi-finite programming, and convex optimization. Now, the simplex can only solve linear programming, right? So that means that interior point methods have upper hand over simplex in that regard. So interior point methods will solve linear programming, quadratic, semi-definite, and even convex optimization. So at this point, let's look at what the Python code looks like for interior point methods. So here it is. You have, of course, here we are using numpy and matplotlib basically. So you have a function defined from line 4 all the way down to line 96. Okay. And what the line is about is the primal-dual interior point, which is one of the implementations of the interior point methods. Okay, so here you define the shape. You have M and the A and A shape. So A is the matrix of coefficients, like we know. B is the right-hand side. And C is that C we have when we formulate the problem. So you have X, S, and Y. So primal variable, slack variable, and dual variables like that. Then you define a mu. You remember that mu that, xi is equal to mu. That's the mu. And you define the beta, which is the shrinking factor for the barrier parameter. So you can increase or decrease this 0.9 and see how it affects the whole system. Then you need to store x values for visualization. That's the x history, and the objective history. Also, you want to store it for the process. So for iteration in range of the maximum iteration, right? You do all the possible things. So and then you print the results at each step, so you can see from first iteration till the end how the result goes. Then you also compute the residuals. That's the difference between what your code is giving you and what the reality should really be. So you have the residual for primal, for dual, and for the complementary, which is xs minus mu. Then you compute the stopping criteria. When should it stop? Like at what point? So you have all of that. Then you construct the KKT system. KKT is Karish Kontoka, which I'm going to talk about in subsequent videos. And then, the whole thing goes, so you can study the code better. You can find it on Facebook. Just copy it from my Facebook page and then try it on your own IDE and adjust some things and see how everything goes. So this is where we actually define the problem. If you remember the problem we had there, I think wanted to minimize CT transpose something, which is, so if you look at all of that now, A itself is 1121. That's, I think, coming from the problem that was stated before we started explaining how to go back. So, okay, I think that seems to be another yeah, for the constraint, right? We have 1, 1, maybe when it has been settled. So this is 1, 1, 4. Let's see how that implements there. So this is 1, 1, 2, 1. Then for B, we have 4, 5, 3, 2. I think this does not have any bearing with this now. Okay, I mean, so in this case, let's take this as a problem of its own, and then you can adapt it to anything you are solving. I guess I did not capture the exact problem there, but this is an example you can actually follow. So if we run this now, this is what we get. But I think it's the same. It's actually the same thing. I'm actually, so 1, 1, 2, 1. Let me see again. 1, 1, 2, 1. Uh, then there's 3, 2 here. So 1, 1. Then all of that 4. I think there's something that should be more clear here. Okay. So the A itself is okay, so AXB, that's for the constraints in particular. All right, so let's see how that goes. And then whatever problem you have, you can then adapt it in your situation. So, I mean, so having run it now, we have the first iteration. You have the x values to be 1, 1. This slack are 1, 1. Y will be 0, 0. And the objective value at that point evaluates to 5. You remember you have 2x1 plus 3x2. So if you put 1, that's 2 times 1 plus 3 times 1. That's why you get 5. You go to the second iteration, you have 1 to 1.95 and it evaluates at 6.9. The third iteration gives 1 and 2.947. So you can see the first one is like fixed and the second one is moving towards something. Let's see. So that's 8.895. Iteration 4 still moving. So we have 1 and 2.9, 8.95. Iteration 5, 1 and 2.9. Iteration 6, 1 and 2.99. So it's like that one is moving towards 3. Now at iteration 9, now we have 1, 3. And that the objective value is evaluated at 8.99. Iteration 10, it's 1, 3. So it keeps, so from iteration 10 upwards, it's not like 1, 3 and it's going like that. It keeps going 1, 3, 1, 3, and the attrition goes. So it's everything is still like 1, 3. So at some point, right? So but other values are adjusting. So then we get to a point where we have 9.0. So 1, 3 and 9.0, that's iteration 14. So after this iteration 14, other things have been adjusted. All the S and X, Y are adjusting. And then we go all the way to 100 iterations. So, and it is stopping there because it has reached maximum iteration because all the other values are still changing. Though you have already got X and Y, one to be 1, 3. So, and if you evaluate 2x1 plus 3x2, you get 2 times 1 is 2, 3 times 2 is 6. So, I mean, 3x1 plus 2x2, yeah. So 2 times 1 is 3 times 1 is 2, then 3 times 2 is 6. So 3 plus 6 is 9. So that's why you have this now. And then, so for a graph, you have this convergence. So it means the optimal solution for that problem is actually 1, comma 3. All right. So in particular, I want to see where the barrier is, the log in this situation. Where is it? Barrier. Where is it here? Barrier. Okay, I think in this case, Karish Kontoka takes care of the barrier. All right. Yeah, I mean, so you can look at this and compare it with your own situation and see how they compare. So from here we see that x1 is equal to 1 and x2 is equal to 3. So that the objective function evaluates at to be 9. Of course, other things, although you still have other moving parts. So you are minimizing C transpose X, which is 3x1 plus 2x2. Okay. So we can make that conclusion that the solution from the Python code, from the Python code, we have x1 to be 1 and x2 is 3, such that the objective function, or that the objective function C transpose X, which is equal to 3x1 plus 2x2 is the same as 3 times 1 plus 2 times 3. So that is 3 plus 6, and that is equal to 9. So the value of the objective function is 9.0, if you like. So in conclusion, right, we can say that interior point methods particularly the primal-dual approach, are powerful tools in solving large linear and convex optimization problems. Now, the problem we have solved here is not large, although it's linear, right? So, but I mean, just like I said, we use most of these numerical methods on very simple problems, so we can see their efficiency in solving uh larger ish problems like that. And coding is usually the way to go. So they offer a polynomial time algorithm and have become the method of choice for many large-scale optimization problems due to their efficiency and ability to stay within the interior of the feasible region. Now, if you look at the iteration, you discover that the problem started from one, two, and then so the one that is at one just stops there. It doesn't go out of one again. But then for the X2, it keeps it's like it started from 2 point something, then 2.9, and then it went 2.9999 until it approached 3, and then other things just continued to change. All right. So that is the interior point method for you. So let's see if you can get one or two practice questions in this line. Practice questions. Of course, you should be able to explain the key difference between the simplex method and the interior point methods. You should also be able to talk about the role of the barrier function in interior point methods. Why do interior point methods stay within the feasible region during optimization? Describe the primal dual interior point method in solving linear programming problems. What are the stopping criteria for interior point methods? All of that, right? Let me just give, let me see if I can have up to two practice questions. Practice questions. Okay. So solve the following linear program or linear programming problem, if you like. Solve the following linear program using an interior point method approach. That is to minimize 2x1 plus 3x2 subject to x1 plus 2x2 less than or equal to 6, then 3x1 plus x2 less than or equal to 9, and then x1 and x2 are both greater than 0. So that's 1. Okay, let me see another one. I found another interesting one we can try. Okay. Consider the logarithmic, consider the logarithmic barrier function for a simple linear programming problem. So compute the gradient of the function that is f of x equals x1 plus x2 minus mu into log x1 plus log x2. So that gives a very good instance of barrier function. So let me see your comment, your answer as a comment on Facebook or on YouTube. Then of course, let me also know in the comments how helpful these videos are for you. And if there's a problem you'd like me to solve or a topic you'd like me to teach, let me also know. I may be able to find time for all of that if possible. Then if you have subscribed, thank you so much. If you have not, please go ahead and do that. And also hit the notification bell so you can always get alerted each time a new video is released. After now, I'll be talking about convex optimization and later non-convex optimization. And then I think we have like 3 or more topics to go before this numerical optimization techniques playlist is done. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.